Okay, so where were we last? It's problem number 10 in chapter 3, right? And we'll get there. Page 80, 88. All right, so a lot has happened over the last few days. A lot of weather issues and a lot of other things happening. And let's just concentrate on this stuff a little while and then get on with life. But this looks like an interesting weather period here for us. Okay, so basically, we're into the clippers and clampers issue, and I haven't looked at this problem exactly, but I wanted to finish this and get into chapter 4 just a little bit today, and so talk about finishing the course. But to be honest with you, it's been an interesting weekend. We went down for my mother's 102nd birthday, and it was on Saturday. We celebrated it. Her actual birthday is this coming tomorrow, but she'll be 102 years old, so that was our primary focus, but a lot of other things happened in the meantime, and nursing home and all that kind of stuff, so we just are thankful to get back and get our feet back on the ground. But that being said, I rolled in last night about 10 o'clock, and it's just nursing homes are no fun, and not that they can't be interesting and good, but they can be very difficult, and people can be very difficult at times. So having to deal with a lot of issues, and just got to concentrate on this for right now. How's that? We forget about all that other stuff and think about this stuff. Okay, so this is problem number 10, 3.10, and draw the output waveform for the circuit right here. So basically, what you have to do in any of these circuits is to take it a point-by-point basis. So you concentrate at a point, and you think about what happens at that point, and then this is a sine wave, and this is what's going on. This is a sine wave like this. And then there's a capacitor, which is 4.7 K, and or excuse me, a capacitor is 10 microfarads and a resistor is 4.7 K. And then you have on top of that, you have a diode, which basically allows flow in the reverse direction. So basically, it allows for flow when this is negative. So when this is negative, this flows, and it gives you 0.7 volts. So basically, when we're negative by more than 0.7 volts, this gives us 0.7 volts. That's all we got to do. That's all we got to know about. When the signal is less than 0.7 volts in the negative direction, and this is pulling it down, and that's got to be even after the capacitor. So this may be one of those that I have to admit I don't know all the details, but let's just look and see what we got. So okay, so when it goes up, it goes to a peak of 5 times, it goes to a peak of 5, okay? Then it starts to decay, but this R and C, it should go down like this, but this R and C cause it to delay. So the RC time constant is a delaying factor, and it is equal to 10 times 10 to the minus 6 times 4.7 times 10 to the third. So you got to say, now, what does that have to do with this? Well, you have to ask, you say, well, it's 470 times, it's 47, excuse me, it's 47 times 10 to the minus third, all right? So that gives you a relative amount of time so that it does this, and it goes, excuse me, it does this, and it gets 63% of the way there, most of it, but it doesn't get the whole, it goes 63% in one tau or one time constant. So it's decaying, and it's quick, and then it starts to flatten out. But this is one time constant, so it's 63% of its final value, and 47 times 10 to the minus third. But this is 2,000. So basically, that is, T is 1 over F, which is equal to what? 1 over 2,000 is equal to 2,000 TED is equal to 0.5 millisecond. And this is 47 milliseconds. So basically, it's not going to decay much. So it's going to start to decay, but it's not going to decay. It's not going to decay a lot. All right. So that's going to happen. Now, what happens when it gets to it's the voltage is never going to get to the point where this is going to turn on and conduct in the reverse direction, because when it gets down to here, it's going to start over again. So basically, it's in one cycle, or 0.5 milliseconds, it's going to decay very little. So basically, this is going to look like this. It's going to be like this, and then down. But the voltage is going to decay very, very, very little from the peak. It's going to start over again, and it's going to do this. It's going to keep doing that. And that's all it's going to say. It's going to do that. Because of this little time period, this quick time period, and this fairly long time constant. So that's 47 milliseconds, 0.5 milliseconds. There's no comparison, so it's not going to decay very much. And that's all that one is. Not a big deal. Okay? And this one is, draw the output waveform of this one, and it is a little bit different. So the last couple problems. Okay, so in this one, draw the output waveform for the circuit. This one's right here. So they changed the variables, but in this case, they put the clamping voltage at 2 volts. And at that point in time, let me see what I should put, what happened with this guy. With this guy, we go to 8 and we come back down. And when it's less than, if it can make it to less than 2, then this clamps it at 2.7. So this would hold it at 2.7 in a negative direction. So basically, 3.11 is going to be a circuit. I personally do not care for these circuits. You never build these circuits. These are just all theoretical, so they're very little practical value. But anyway, so it goes, the input goes again to 8, comes down to -8, goes back up to 8, that type of thing. And the frequency here is every 2 milliseconds. See, the frequency is 1 over 500, or every 2 milliseconds. And the time constant, RC, is equal to 4.7. He likes 4.7 times 33K. So that is equal to 4.7 times 33 times 10 to the minus third, or what, Ted? That is equal to a very long time constant. So it is equal to 3K. That's pretty long. 155 milliseconds. So basically, this is going to be very much like this. And I don't, I'm going to have to look at this one. I'm not going to give you the final answer on this one. I'm going to have to study this one. I'm sorry, but I'm going to have to study this one and look at it some more because I have not worked on this one before. So I'll give you a better answer on Thursday on this one. I apologize for that. Okay, now on to something that I know a little bit more about, not a lot more, but a little bit more about than clippers and clampers. And this is BJTs. And this is an interesting subject because basically these are things you can actually use. And I do, not a lot, but I do use them in circuitry and stuff like that because sometimes you just can't get there without using these in a circuit. And I'm honest when I say I'm not good at this, but you don't have to be really good to at least kind of see what is going on with the bipolar junction transistors, okay? Now, I taught 3050 for quite a while, EET, or ENT 3050, which basically goes through the resistive and reactive course in one semester, and lightly touches on the subject that we're talking about right now. So basically, I wanted to go through that and show you how I taught this subject for them. Okay, so let's go back. Look at that. So in that situation, we have to get through a lot of stuff in a hurry, and those folk do not have the privilege of being able to take their time and go through this stuff at a more leisurely pace. So they only get a little bit of time, and that's why this is very important to them, because they need to get a fresh understanding, but not a lot. Okay, so this is a picture of a bipolar junction transistor. All right? You may not believe that, but it's the truth. All right? So now, what do you want to do in an amplification circuit? You want to be able to have a device that can control the flow that you can control yourself, okay? You can control this. You can turn this handle and you actually leverage your hand into regulating a force that you couldn't regulate otherwise. So this handle here gives you the ability to regulate the amount of flow out of this faucet. Everybody agree with that? How many of you have turned the faucet totally on and then hold your finger over the thumb and tried to regulate the flow that way? How does it work? Not well. Okay? So if you have a method to regulate the flow that you can control with your hand or your ability, that makes all the difference in the world. Okay? And this is a picture of that. Okay? Little flow, big flow. Okay? Little bitty, big big. Okay, that's that. Okay, now, also in this device, you have a load line. Picture a baseball diamond with, how many of you have ever seen or heard of the Green Monster in Fenway Park? I've never been there, but everybody hears about it. Everybody realizes what the Green Monster is. It's a wall out in left field that if you hit it over, you get a home run. But it's not very far away, but it's pretty high. So it's the temptation is to hit a home run over the Green Monster, okay? Well, picture a baseball field with high walls down the left field wall and the right field wall, okay? A right field line and a left field line. So you can only hit the ball into the field of play. You cannot hit a foul ball out here, you can't hit a foul ball out here. But if you hit it along if you hit it like it's going to go out here, it will go along this wall and just go. All right? If you hit it along this wall, it'll just go down that wall right there, okay? Now, you may not think of it that way, but this is called saturation and this is called cutoff. All right? So if you hit the ball along here or along here, you're acting as a switch. It's either totally on or totally off. If you hit it out in the middle of the field, it's acting like an amplifier. It can either go this way, or it can actually be used as an amplifier in the middle, out in the middle. This is called the load line. So from cutoff to saturation, you draw a line, and along that line is where the ball is going to hit. It's going to hit somewhere along this line. It's either going to hit here, it's going to get here, or it's going to hit somewhere in between. And that's a bipolar junction transistor. It's like a baseball field. If you don't like it, that's my analogy. And it kind of sticks in my mind because I can see the baseball field where you can hit the ball down one side or down the other. That's like a switch. Or you can hit it out in the middle of the field. That's like an amplifier. All right? Now, what is the rule of thumb? What's the rule of thumb for this? Okay, well, for this little simple circuit like this, for every 5 volts, if you have this has got a 10 volts, but if you have 5 volts up here, and this is 1K, it'll act like a switch. 5 volts, 1K. What about 24 volts? How about 4.7K? It acts like a switch. So if you ratio from 1K and 5 volts up, you get this thing to act like a switch. If you add more resistance, it will start to act more like an amplifier. So if you start thinking in terms of making this a switch, what do? Look at your voltage. What is your voltage? What is this voltage right here? If it's 10 volts, what would this be? 2K. The other thing that's weird about this is this. It's backwards. In other words, if you turn this on and put a voltage, a positive supply here, this goes to 0. If you put 0 here, this goes to the voltage of the 5 volts of this output. So it's just backwards. Okay? Other than that, it's just an ideal switch, except for the fact that it's backwards. That's it. It acts like a switch when it's here or here, okay? This is when it's on, this is when it's off. That's about it. So if you picture a transistor as that, right there, a bipolar junction transistor is that right there, you start to get an idea of what's going on, okay? Make sense? That's what it is. Now, what is this that's coming out? Bipolar junction transistor is current. In an FET, it's voltage. So the older style and by the way, why are we now in the FET world, in the field effect transistor world? Because there's very little or very high impedance and very little current. So you don't get the heat that you would with current. These devices would build up heat. So we got away from bipolar junction transistors and we went to field effect transistors for that very reason. The heat buildup of these guys is tremendous if you use them in mass, like in thousands and millions and billions of these things in one little area. So you don't use a bipolar junction transistor hardly ever, except for individually, but they're the simplest ones to use. And that's the simplest one you can use right there. But if you see that, put that in your mind, don't let it go. You can't be shaken. All right? What are we trying to do here? trying to amplify the amount of water we get out by turning this handle. Little force, big effect. It's an amplifier. All it is. It's simple, but yet very profound. All right? And that's how I teach bipolar junction transistor. So again, we're going to go through this in this chapter, and we're going to learn more about this because there's more than one circuit. Obviously, there's a bunch of different circuits, but that basically is it. If you can get that and you're, focus, you've got a lot of conquered. Now, when I was undergraduate, we had a hard time because everything had to be proven, and there was a problem with bipolar junction transistor circuits, and you had one more variable than you had equations that you could write. So there were no approximations. And I was very curious when I got assumptions. And they do, and that's part of this course is you make a couple of assumptions and you get on with life. But in that era, and I'm sure they're way past that era today, you couldn't just make an assumption. You had to be absolute about everything. And it worked against you in order to be able to actually calculate the resistance it would take to make a certain circuit work in a certain way. My point is this. I learned how these things worked when I was teaching them in electronics. So I was not good at this circuit stuff until I got to teaching it, and I had to learn about it. Okay. So there is this energy hill in an NPN transistor as well as with a diode. And it has to be overcome in order for it to work. And it does the same basic effect as the diode. Now this area of P is very thin, but this is what the base is connected to. So the base is it's the handle on that faucet. The more voltage you put in here, if you bias it positively, that it will allow current to flow really from the emitter to the collector, but we know that positive current travels the other way. It goes from C to E, okay? So anyway, electrons actually flow based on the bias of the base. So this guy is the handle on the faucet. Okay. And they show this so this is where where the P region actually controls the flow from here to here. It goes through here, but this controls that flow. All right, now, if you have a NPN transistor, you can test to see if it works kind of the same way you do a diode. And I don't remember talking to you about testing a diode, but you have to put the voltmeter on a high ohms scale. Do not put it on a low ohm scale or you'll blow it up or you'll destroy it. But if you put it on a high ohms scale, if you turn it one way, it shows low, and if you turn it the other way, it shows high. So with the transistor, if you use the base, you go base to collector, base to emitter, it should show low. And if you go emitter to base and collector to base, it should show high. All right? If it doesn't, it's blown. So in other words, a cheap way to test to see if a NPN is working is to see if you get the same high-low effect. It's an easy way to test to see if they're working or not. All right. So I don't really care for this right here, but anyway, let's just keep on going. So okay, so in this circuit, we have the B, the E, the C, the B, and the E, all right? And the ratio of these is currents. They refer to them as alpha and beta. Beta is the more important one, but alpha is, well, you can see that the relationship here. Beta is the relationship of this current to this current. This is how much force you put on that handle versus how much water you get out. In other words, little force here, big response here. Just a little bit here gives you a big change here. And that's one of the ways you do that. But you've got to get a current flowing from here to here. And in order for that to happen, you have to go higher than the 0.7 volts. Because from here to here is this electron hill. So if you climb above 0.7 volts between this point and this point over here with a circuit over here, if your circuit over here, the relationship between B and E is more than 0.7 volts, you do get a flow of current in this direction, depending on what is all back here. And then the ratio of this current to this current is the beta. Now, what is beta? It's usually about 100. So you do get a lot of amplification of what you're doing over here. So if you're doing a little bit over here, you get a lot over here. That's why it's called an amplifier. Okay? So the beta effect is what you put in versus what you get out. And it's 100 or 120 or 150 or 80 or whatever, but it's a lot. So the amount of force you put on the handle of the faucet versus the amount of force of water you get out is little, you get a lot out. Okay. So that gets you an idea of the picture. This is the handle, and this is the water supply, and this is the output. This is the faucet coming out. It's a little bit of but you got to get above 0.7 volts in order for it to work. Okay. The PNP version is created by swapping the material of each layer. The outcome is the logical inverse. Okay. Conventional current flows into the emitter and out of the collector and base. So this is the opposite. Basically, if you stick with NPN, that's what I pretty much do exclusively. But again, anyway, stay with NPN. How's that? We'll get the NPN down and then we'll worry about the PNP. All right. Now this shows this ball field. Here's my current. Here's my voltage across the VCE from collector to emitter. All right. And these are amplification areas. This is where this is saturation area. And this is shut off over here. This is excuse me, down here is where it's shut off. This would be a open circuit or no flow at all. But this over here would be a family of curves showing as VCE gets bigger, the amount of current. And this slope of this, I think, is the beta. Not sure. So this is the saturation region over here. This is the amplification region. And over here is your shut-off region. Breakdown region. In between these two extremes is a region where the collector current is relatively constant, showing only a modest positive slope. This is the constant curve region. This is where we want the transistor to operate for applications such as linear amplifiers. Now, in these circuits right here, if you're operating this area, what you have to have your DC bias to set it up. But when you're amplifying or when you're changing, if you have an amplifier, what are you actually trying to amplify? You're actually trying to amplify something that is, it's not a sine wave, but it looks like a sine wave for the most part. So you're trying to amplify something that you're trying to amplify your voice. You're trying to amplify somebody's music or something like that. It's really not a sine wave, but it looks like a sine wave, and it oscillates around a point. Okay, it oscillates around a point like this or whatever. It oscillates around a point on this graph. Now, if it gets too large, it gets over here or it gets over here. And you've heard this before. When you turn the volume up too high, you hear what? It cuts off some of it, doesn't it? You've heard that. It cuts off some of either the high, you don't hear the whole sound, you don't hear all the sound. You hear what sounds like the same thing, except that it's garbled a little bit because you don't hear the full song, the whole thing. So what you're actually doing is you're clipping off part of this and part of this. And that's because it's running into this wall or it's running into this wall. Okay. See, oscillation around a point has to still be in this, it has to be in this area. It cannot go beyond here. It can't go beyond here. So that's what you're actually hearing. It's saturated. The sound you're hearing is actually saturating. Okay. So again, are you interested in transistors as switches or amplifiers? For the most part, everything that we do here is amplifier circuits, but we also consider switches, so we have to understand both. But most of the time, we're talking about them out in the middle here where they're being used as an amplifier. Okay. So now we get into the math. Okay, so this is beta is the ratio of the big current to the little current. So here it is. This is this amplification of the current. It's 105. All right. In that case. Now, can this change in a circuit? The answer is yes. And the more stable the circuit, the more sophisticated the circuit is, the less this will change. It can change with heat. It can change with other things. But if you put a circuit together right, this will be fairly stable. All right. So this is a transistor, and you're using transistors in your project as a switch. You're not using it as an amplifier. We just picked one up, put it in there, let it rip. And we use the fact that it turns on and off at 0.7 volts if we bias it correctly. Okay. So this Ebers-Moll model is this device right here. Okay, so it's a kind of what I've been saying. It's a, if you have a current coming in here, this is that current times beta. And then you've got a diode down here, which drops you 0.7 volts. So in other words, if you can find the voltage at this point, then the current coming down through here, if you can find the voltage there and find the current here and know the beta, you can find the current coming down through here, or the potential current coming down through here. This is called a common emitter configuration. There's a lot of different ways you can draw this up, but basically this is one way of doing it. Now, in most cases, what they want to do is the output is right here. This is where the output is drawn from this circuit. Okay? And again, it is upside down with regard to a switch. If you turn this on, and this is forward bias, and this flows, this will go to 0 volts, which is opposite. You'd say, high, this should be high. No, this is low. If this is low, in other words, less than 0.7 volts, this will be high. So again, he goes through all these parts and pieces, and he says, now, what is my relationship here? What is my... This is the voltage over here is the battery voltage. Again, this is just a biasing voltage. Here's a resistor, and here's my base. And then if I'm over 0.7 volts here, I'll flow. And then this will flow at the ratio of this times this will give me the current through here, and then this will give me the if this will allow that. If there is enough voltage and the resistor is not blocking it, it will allow that amount of current. Now, if you can't get that amount of current out of it, what happens? It's just basically an on circuit at the point of this divided by this. In other words, what's the maximum current that can flow through this device? It's this divided by this, period. So you can say this beta is this amount times this, except for the fact that this can overrule this. You can't go higher than full on. In other words, you can't turn the handle of the faucet more than full on. And that's what this is. This divided by this gives you full on. You can't get more than that out of here. And you run into a block, and that's it. So again, there's rules, and then there's ancillary rules, and you got to kind of look those over and get those that way. Okay, so that's, you got to be constantly thinking about, but I can do this, but I can get the current here, but it can't be bigger than this. Which is true. Can't be bigger than that. Okay, so this drop of this voltage here is from here to here. It's not from here to here. So this voltage really is the drop. This 0.7 volts is in this circuit right here. Okay. So now they've developed some rules, right? They've got some equations, and now they're basically saying what? VBE is 0.7 volts. And so I can now start calculating my current, and I can do my beta, and I can now see if I've got, if my beta is, where I'm at on my load line. So now we get into some real problems. Okay, so this is a real live problem. Right, so if VBB is 10 volts, VCC is 15, RB is 200K, RC is 1K, and beta is 100, assume that it's the transistor silicon. So that basically is saying 0.7 volts. By the way, you're going to thank me a million times over for what? Allowing you to have multiple study sheets, okay? So these problems, these formulas, you do not have to memorize. Thank you, Professor Evans. It's a huge, huge, huge gift. You do not have to memorize these, but this is a standard way of solving this problem. You find IB, VBB minus VBE, 0.7 volts. There's your 10 volts minus 0.7 volts. There is your IB, 46.5 microamps. So basically you start with that. Then you find IC, okay? Then you find beta. You look at beta, and they give you the beta, 100, and that gives you the current at that point through the IC. So now you know the current through the IC. So now you can go back I like it when we get to problems because why? Now, all this stuff can start to make sense. So here we are with this circuit. We got a voltage supply, VBB of 10. We've got a resistor here, RB of what? 200K. Got my transistor, my NPN transistor, and I've got a resistor up here, and I got a voltage supply. This is called VCC, okay? So I come down here to ground or to 0 volts. Now, in this case, we find IB, in other words, the current flowing in there into the beta and into the base is equal to 46.5 microamps. Now, by definition, IC cannot be, it's 100 times that. Which is going to give me what? 4.65 milliamps. So now I know the current going down here, 4.65 milliamps. Now, that cannot exceed this divided by this, but it doesn't. In this case, why? Because this is 15 volts, and this is 1K. 15 volts and 1K is what? What? 15 volts is what? Well, 15 volts and 1K is, that would be what? If I wanted to know the maximum current that could flow down through there, it would be 15 divided by 1K, or 15 milliamps. But we don't have that, we have 4.65 milliamps. So what is, this only soaks up 4.65 volts. So what's left? The voltage across here. This is called VCE. Okay. Now we get to our graph, our ball field. This is our IC. IC to the blind man. This is VCE. I don't have anything neat to say about that, but anyway. IC said the blind man as he picked up his hammer and saw. Did we get? Did everybody? No. That didn't shake you. No. This is IC. This is VCE. So I'm on this load line. What would be the maximum that I would get? 15, right? I get 15. This would be the peak. It would be 15 milliamps. That would be if I was on saturation. What would be VCE? 15 volts. Where am I at on the ball field? Where did I hit the feet? Where did I hit this thing? I hit it about right in here, which is maybe, no, I hit it more over like this, right? It's at what? 4.65 volts, excuse me, milliamps. And what's my voltage? Well, it is 15 minus 4.65 or 10.33. 10.35, Ted. So I hit it to second base. That's a dumb way of saying it, but it's what I did. I hit it to second base. I hit it slightly off to the right. This would be the perfect middle point. Who cares? That's how that's done. Okay? So between the faucet and the ball field, I think you now have some pretty good analogies to how you see this. All right. Any questions? Hopefully that makes sense, because it should. Most people, even non-electrical people, get this. After you show the ball field and the water faucet, they kind of get, oh, it's like a ball field. Oh, it's like a water faucet. Oh, okay. And the fact that you don't have to memorize these formulas, you're in pretty good shape. All right, so that gives you a little bit of an idea. So there's a major problem with the circuit, namely it lacks stability of the collector current and the collector emitting voltage. As we shall see in upcoming chapters, it is important to keep these parameters stable in order to ensure consistent performance from many kinds of circuits. As we noted from our inspection of the blah, 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 blah sheet, the variation of beta bit can be quite large at a given operating point. If we also add in the variance due to the temperature and other factors, in other words, when this thing gets hot, this beta goes all over the place. So it does change. So you've got to protect against that. Okay? What if beta changed to 200? Well, whoop-de-hoo, it would. If beta changed to 200, what would have happened? It would have gone way up here, wouldn't it? Or it might have gone all the way up here. I don't know, but it would have changed. Okay. So, is everybody ready to go out and build their first bipolar junction transistor circuit? You are, by the way. That's one of the reasons I wanted to get you here, because I want you to understand what you're actually building a little bit. Because what you're doing in your project is you're using a BJT to turn on a relay. Is that what you thought you were going to be doing, or is that what you didn't? Did you have any idea? So the thing up here does not have to be a resistor; it can be a relay, and that's what we actually did. We make that a relay. Anyway, what's the resistance? I don't know, but it works, and it doesn't blow it up. It works quite well. Okay. The only way that works is somehow if the bipolar junction is transformed magically into a 3.6 volt battery. No amount of prayer or Cassandra will make that happen. Okay, so this tells you now what I've been telling you all along, that there is a load line. Okay, VCE is VCC minus ICRC. And that gives you where you're at on that line. And that's called the Q point. I didn't give you that information until now, but there it is. That's called the Q point, or the operating point. And around that point, you can build an oscillating AC signal, which will amplify that signal, okay? It will serve as an amplification for any signal you put in there. That's how you get a radio to work. You amplify that signal. Okay. What you actually do is you put an AC circuit in on top of the DC circuit, and it actually does that very thing. And that's how they move. There's your one, there's your other. Easy. Okay, so as a case, what I just talked about was what? Using it in saturation and using it in cutoff. So here it is in practice. So now you're going to see that this guy here turns on when this turns on, and it turns off when this turns off. Well, you just said the voltage here, if you want to use this voltage for something, it's the opposite. Yeah, I did. But this turns on when this turns on. Why? Because when this turns on, this goes to 0 volts. In other words, VCE goes to 0. You're operating right on this graph when you're on. If you got this IC VCE graph, if you got that in your head, when you're on, you're right here. VCE is 0. IC is up here someplace. Your VCE is 0, but your IC is up here someplace. The VCE is all the way to the left. It's not. Here's your IC voltage. This is what it is. Now, the other thing about semiconductors is this. Is it ever absolute? No. Nothing is absolute with semiconductors. 0 is not really 0, it's 0.2 or 0.1. On is not 15, it's 14.7 or 14.8. All right, if you don't believe that, Allen Bradley, the vaulted company Allen Bradley, when they were designing their switching circuits for 110 volt inputs and outputs, they basically had an input card and they had an output card. So here would be my output card, and here would be my input card, and another PLC someplace else. So I wanted to send a signal from here to here that said, I am on, recognize the fact that I'm on, right? If I'm off, recognize the fact that I'm off. Okay? You can use 110 volt, what they call a triac. What is a triac? It's the switch. It's a semiconductor switch that acts like a relay that turns on the voltage, turns on the current when it's on, and it turns off when it's off. Okay? So a triac does that for 110 volts, on and off, solid state. It took them 3 revisions of their output card or their input card to basically be able to read this, that it was not always on. In other words, when this was off, it's not totally off. There's a little bit of leakage out of it. It's not totally off. It's almost off. But this read it as on. Say what? You can't turn your own inputs and outputs on and off? It took 3 revisions. It took 2 revisions. They did the original design. It took 2 revisions to get it to work. Everybody follow that? The irony of that? So what we had to do in the day was to add a bleed-off resistor to ground, about 50K per, I don't know, but you'd go to the closest Radio Shack, and most of you don't even know what a Radio Shack is anymore. How many of you have ever been to a Radio Shack? One. The only other person in here is, so you'd go to this town where the plant is, okay? So we'd blow into town, you'd find where all the fast food places were, because you knew you're not going to get a good meal for a while, because you didn't have time. You just go and, get a quick meal, and that would be it. And the other thing would be to find the Radio Shack. And you'd buy up all the 50K resistors in the Radio Shack. And every time this happened, you would put a 50K resistor to ground, and it would start working. So, in other words, we knew the problem. You had to bleed off the excess so that the input would see the output for what it really was, not for what the leakage current was. So these things are not perfect. There's nothing exact with semiconductors. They're good for most cases, but on the edges they get kind of weird. Another one in my thought processes for this morning, what I will relate to you, and I'm trying to get through this and give you the basics without totally confusing you or making you uncomfortable, but yet giving you some basic that I've grabbed onto, because believe it or not, I'm not the world's expert at this stuff. If you haven't figured it out yet, I'm not. I know enough. I passed the courses, but as far as me and the physics of semiconductors, that did not impress me as something that I really needed to know. I needed to know what? How to make them work in a real circuit, and that's basically all I really needed to know. In a steel plant, you're looking at an input point on a 110 volt input, okay? You got a wire coming in, and you're reading that to ground. So you got your voltmeter from there to ground. What is a 1? If it's on, what is an on? It's a steady 110. Doesn't vary. What is an off? Or zero? What is a zero? What would zero be in a steel plant? Where they have a where they're melting steel with giant currents. In other words, where there's noise like crazy in the plant. I mean, vast amount. I'll think of it in a second. Not a reheat furnace, but it's where they're making steel, the real deal, where they're making it from ore. Blast furnace, where they've got a blast furnace going. What is a zero? Well, it's when it's zero, when the voltage is zero across the current, across the meter, right? No, it's when it's dancing. It's 30, 80, 20, 50, 90, 20, 10, 30, 50, 80. It's all over the place. What are you picking up? The noise from the blast furnace. But it's not steady at 110. That's a zero. It's not zero. It's noise related because you're picking up from everything else. I thought you'd like to know that for what it's worth. Things don't work the way you think they do. They do work sometimes, but they don't work always. And that's one of the places where you walk into it and what is going on? A zero isn't a zero. Why not? You're picking up a heck of a lot of noise. Anyway, any questions anybody's got? Any questions anybody? Okay, now let's go back and figure out where are we at, because I honestly, since last we met, I have let's go back and look at the syllabus, see where we're at. How many of you got the circuit working so far? Anybody got it working? One. Okay, very good. Two. So ready to show it to me? Anytime? You don't have the time delay part? You got the time delay working? Time delay's working? The whole thing? You got the whole thing working? Okay. Okay. No problems? The circuit worked? I knew it'd work. I had put it together before, but anyway, I didn't. I knew it would work. I'd done it, but it's just, how many seconds do you have time delay?
6.
6? Okay, yeah. The difference between this year and last year was, last year I said, oh, if you can get the time delay working, that's okay. If you can't, just make it go back and forth. This year I said, you've got to have the time delay. So if you're calling me mean, okay, but I want you to get that circuit in there, and I know you can. See, that's the difference between having 5 people in a class and having 15 or 20 people in a class. I can ask you to do it, and you'll get it. They just said no, and I can't, whatever. Okay, so we're at this point right here. We are the 14th, review chapter 3, and then next time we are in session, we're going to do chapter 4. So we're actually ahead a little bit, and then chapter 4 is problems, and we'll work on those on Thursday as well. And I'll solve those problems, those other 2 problems for you. I'm sorry that, I think I'm missing something. I'm not really sure what I'm missing. I got to go back and read what he wants, but they're not worth, those problems are not worth your time, okay? I hate to say that, but most of the things in this book have meaning and are used, but I've never used any of that stuff. They're just there to kind of, they're like brain teasers. They're there to confound you, and that's as far as it goes. I don't, but you need to see it, but then get on with life. Okay, so that's where we're at. And then on the 21st, general review, which basically what? How do I, what's since we first had our first tests? Bunch of stuff, right? We've gone through a bunch of stuff, all right? But I always go back a little bit and dip into the stuff we had before. So we kind of do that a little bit, and then we go ahead. 10 questions, same as it was before, anyway. And then the final exam is 8 to 10 on the 28th. It's comprehensive. So what do I do for the final exam, for our final? I take your 2-hour exams and I look at them and I say, where were the problems that most people had a hard time with? And I put them on, and then I may put another couple questions on. It'll be the same kind of thing. It'll be 10 questions, but I put the problems on that everybody had problems with. So if you think that you got away from something, whoop, we'll have to do that again. Nope. One more time. And this time, hopefully you get it right. That gives you a chance to redeem yourself, and it also gives you a chance to get a better grade. Because I'm not going to vary from it very much at all. That's my theory. It's how I stick. That's pretty much how I stick to it. I'm not going to throw any curveballs or anything like that. This is pretty straight down the gut course. It's just, this is what it is. And, you say, well, there's nothing in this course that you can't get in something else. Yeah, there is. There's only one other course, by the way, that you can get this stuff in, and that's in the EECS department. And they're the only other people that are going to talk to you about this stuff. So we do the same thing as they do for the most part. And they don't talk about ball fields. They talk about more theoretically. I cut it down to something that I can relate to, and ball fields and faucets. I'm serious. I get that in my head, and I can understand that in my head for what it's worth, and I can carry that around with me, and I understand it pretty well. Oh, that has nothing to do with physics of semiconductors. Nope, it doesn't. But I can grasp onto it, and I can understand it, and I can then do just about whatever I want to with it. So, anyway. Any questions anybody's got? Take care. We'll see you. Oh, by the way, I haven't graded anything, so you